안녕하세요. Hi, I am Garima Jain, and the title of the talk is A Lot of Image Filters on Android. I am from India and I'm also an Android Google developer expert, and I work for a company called Hoppr. And when I say a lot of image filters on Android, I literally mean it. So, this talk is going to be about how we implemented a lot of image filters for our app called Hoppr, which is a content creation tool for GoDaddy, wherein we can have things like text over images, text over video, and we can, which also comprises of like these filters. So, who is this talk for? If you have done any kind of image processing on Android, then that's great. But if you have not done any image processing until now, then that's even better, because like this talk doesn't require any knowledge of image processing and all those things to understand the concepts that we're going to talk about. So what is this talk about? You must have seen various apps like Beauty Plus, Google Photos, Instagram. They provide us with an enhanced list of filters that we can choose to enhance our images. For example, like this fruit filter over here, toast, like all these filters internally apply a bunch of algorithms and change our input images magically to look much better, or like we just have like option to make our input images better. And certain apps also provide us with these advanced tools of like picking, for example, hue, saturation, luminance. We can also tweak various curves and all those things to improve our images. So all these lead to a filtered output image. So this is all of this comprises of like applying filters to images. So what we are going to talk about in this talk is like different approaches to filter images. Then we'll briefly talk about what are LUTs, like how we can apply an LUT image filters to an input image. We can do that using Renderscript. That is what we're going to talk about. Then we'll have a look at what are the various challenges that we faced while implementing LUT image filters. Then we'll also briefly visit the OpenGL implementation of LUT image filters. So without further ado, let's jump right into the first chapter of this talk, that is different approaches to image filters. So we have different kind of approaches that we could have taken for these filters implementation. The first one is presets. Second one is the lookup table, and as you might have already guessed, we went with lookup tables, but let's also mention like what this presets one is all about. So recently I just showed you these screenshots from this Adobe Lightroom app, wherein user had the option to select and change the input image according to various different options, which is great. And these kind of options are actually presets. And these filters, like the way these filters are stored and implemented is designer applies all these complicated values, and then these values are stored as a data structure of like these combination of saturation, sharpness, luminance, vignette, and shadows and contrast and all those things. And this means that like if we take the example of our app, like we have not just Android, we have iOS app, we have web app. So all these different platforms need to understand how to apply, like how to interpret this saturation value, how to interpret this sharpness value, and all those things. Which means like if there is any particular tool that a designer wants to use, and for example at some point they decided that like let's try out this new tool which has this new complicated option. So it might be difficult for them to add a particular different kind of preset to this data structure, because that particular preset, then each platform needs to know how to implement that particular preset. So presets are good, like it gives users a bunch of options, and from product point of view, like our tool, like at that point there was no use case for user. Like what we aim to do is, like, we want our users to be able to quickly create some content, like and easily, but these options could be overwhelming for certain users. And also, like, having a bunch of different options means that, like, it was hard for us to ship faster, because we had to implement all these different options across different platforms. So I agree, with presets we can achieve great results, and the user has a lot of customizable options. And but, like, do we even need it at that point? So after different analysis and everything, we figured out that, like, this is not the option for us, and if we wanted to ship faster, then we had to choose a different route. And that is when we come across this different route of using LUT, lookup tables, instead. So what are lookup tables? Given an input image and given a lookup table, what is, like, for each pixel in this input image, what we're going to do is, for example, like this pixel, we're going to look up this pixel in this table, and this pixel is then going to map to this different pixel, and finally we're going to do the same thing for all the pixels in this input image, and finally we'll get a filtered output image. Like, instead of implementing or interpreting how to interpret, like, all those values, like saturation and all those things, and then making it consistent across different platforms, we just need to implement this LUT lookup algorithm, which should be the same, like, which should be achieving similar results across platforms. We just have one algorithm to tweak, and this is, like, what a lookup table is. So this lookup table, what it does is, it replaces runtime computation, that is interpretation of all these elements and whatnot, all these values, with simple array indexing operations. Like, this lookup, this is actually a very simple array indexing operations, because lookup tables are simple arrays stored in memory, and we can, like, for a given RGB value, we can look it up in that, like, array. So we have different types of lookup tables: 1D, 3x1D, and 3D. So this is a very simple 1D lookup table, which is essentially an identity lookup table. We have, like, just these 4 values which we are storing. So 0 intensity maps to a 0, and 1 maps to an 85, 2 maps to a 169, and, like, we get this, like, we get this output of simple identity lookup table. Then, because our images are not simply black and white, we have three channels to map, so we can instead use 3 identity lookup tables, like, one for each channel. Like, all the values of R will have all 256 values to map for, so we'll have, like, 3 arrays, 1 cross 256 arrays, like, that would be the 3 different lookup tables. But this is actually not what we need. What we instead need is, for each combination of RGB values, we want to map to a value in this 3D range. So instead of 3 different tables, what we need is one 3D lookup table. This is what we need, and this is how it's going to look like. So currently, this is an example of a 3D identity lookup table of dimension 4x4x4. So given an input RGB value of 0, 0, 0, which maps to black, and 3, 3, 3 maps to white. So this is our identity lookup table, as you can see. So currently we're only assuming that R can take only 4 values, but in real lives R can actually take values from 0 to 255. So this kind of a lookup table is pretty limited, and practically in real lives we use 64, 64, 64 LUT images. Then you might be thinking, why not just use 256 cross 256 cross 256 images? So we could do that, but like then those LUT images will be very big, and like for practical purposes, like we have noticed and we have realized that 64 LUT images are also just enough, and like they work out for pretty much most of the use cases. They can map about 64 cube colors, and which has proven to be pretty fine for our use cases. So this would mean that, because like instead of 256 mapping 256 color, we're only mapping 64 color. So so 4 colors at some point would only map to to just one color. Again, the next 4 would just map to one color. So this is something to keep in mind. So this is how our 3D square LUT image looks like. So in order to understand what's going on, like what all these boxes are, let us have a look at this 3D LUT in more detail later on. But for now, let's understand how this 3D LUT image fits in designer's pipeline. So designers create filters. They use all those complicated tools, and like they tweak those curves for us, they apply all those values, but they apply those on these identity lookup images, lookup tables. Then they apply each of these values to different lookup tables, and then they export these to create new lookup tables. So I hope you got the point. Like they start with the LUT image, they apply a bunch of filters, like using the whichever tool they want, they export the image. So this is a new LUT that is created, and we can then use this particular LUT in our apps and use that to look up colors from our input image to map to a different output filtered image. Like if it is still hard to figure out, then do not worry, we'll have a look at it in detail later on. So by doing this, designers can create a lot of image filters and we can use them. But how we can do that? Now this is something we are going to look at. So firstly, like when I started researching about this, like I came across this library called easyLUT library, and I cannot tell you, like the bounds of my happiness was like I was so happy that I found this solution, something available out of the box, and I should be done. And but this happiness was short lived, because one of my colleagues, she pointed out that this easyLUT library internally uses something called getPixel and setPixel, which are Java functions, which basically what they do is they iterate over each pixel, and they do it on CPU, and which is pretty slow. And if you want to learn more about it, then you can have a look at these talks, like efficient image processing on Android, practical image processing in Android. At that point I was being naive and I had not watched all these talks. I should have, but anyway, like then I went and watched these talks, and I understood various different images to different approaches to image processing. So the gist of all that is, like there are various ways. In Java we have getPixel and setPixel, which is not fast enough. Then we also have another option called Renderscript, and then the third option is OpenGL. So at that point our tech stack was already using Renderscript, so I went ahead and started to look into how different approaches that we can use to implement LUT image filters using Renderscript. So there are two ways of doing this in Renderscript. The first one is baked in intrinsic. So there is this class called script intrinsic 3D LUT, which is available to us in order if you wanted to implement lookup tables in Android. The other option was also there, like using a custom script, but we'll get back to that. So firstly, let's look at this first option, script intrinsic 3D LUT. So this is its definition right out of developer Android. I usually do not post such long paragraphs in on slides, but like just the purpose, like just for the purpose of this talk, I'm doing this. So let's go word by word. So what this does is it is intrinsic for converting RGB to RGBA by using a 3D lookup table. Looks like what we need. The incoming RGB values are used as normalized XYZ coordinates into a 3D allocation. Not sure what that means. The 8 nearest values are sampled and linearly interpolated. Looks like exactly what we need. And then the result is placed in the output. Great, we do need the result. So this looks like what we need. So I went ahead and looked at the APIs that we can use. So there was this function called setLUT, which takes in an allocation. Allocation is actually Renderscript's way of doing malloc and calloc, like allocating some memory. Renderscript uses C99 under the hood, so it doesn't deal with malloc and calloc. Instead, it uses this allocation. So that is fine, but how do I create allocation? And it turns out there are a bunch of different methods that can be used to create allocation. That is create cube map, there are create from bitmap and whatnot. So how do I convert this given LUT image into an allocation? Like which function should I use? So I started researching into it, and after like some time I still had no clue. But then I came across this helpful piece of code on GitHub, which is called easyLUT library, and from that I could figure out that I had to use this create typed function, and a bunch of hidden trials later, and then figuring out that we couldn't even use the square LUT, and like all those like hurdles were still there. I figured out that like a way to convert LUT into an allocation, and then it was just a matter of these few lines. Like I created my LUT allocation, I create the script intrinsic 3D LUT, and then the script can run for each, like this allocation input is the input bitmap and out is the output bitmap, and this particular for each runs for each pixel, and Renderscript makes it run parallelly, and if GPU is available it makes it run on the GPU. So that is good, and this is all I had to do, and I was really happy that it worked. So because I told you that it has to work across different platforms, like it has to work on iOS as well, it has to also work on web. So my colleagues from another platform, they created a certain test, and one of those tests was this transparent test. So after it worked, I went ahead and started applying those tests to my outputs, and it turned out like this was the transparent test. Like what let me first talk about what this transparent test was. Transparent test is like, given an input image, if there were certain transparent pixels in that input image, then what will happen, like so if you remember, we had an input image and we would look up its pixel value in the lookup table, but like input image also has alpha, so it should work fine. But turns out my algorithm failed, and it turns out like script intrinsic 3D LUT to the extent of my knowledge did not support alpha values in input images. They should have put that in the in the reference in the documentation, and it turns out they did. I just couldn't find it. Like, it looks like they are trying to say the same thing, like it's converting RGB to RGBA. It's not taking input as A. But like, even today I'm still not sure. Maybe script intrinsic 3D LUT can still use alpha values also, but I just couldn't make it work. So if you are able to make alpha work with script intrinsic 3D LUT, then please ping me. I just it would just like give me some kind of satisfaction. But anyway, like then we come to the next approach, that is using a custom script. Actually, like, script intrinsic 3D LUT, as the name suggests, also uses script behind the scenes. Anyway, we are talking about Renderscript, so everything is a script with it. But yeah, like, so it has this like baked in script, and instead of using that script with custom script, we can use a different script which we can create on our own. So what our custom script needs to do is, like, it needs to take each pixel value RGB and find the corresponding value in the LUT image and use that value instead of using our previous pixel value. As simple as that. So let's try to depict this with a diagram. So we have our input image and we have our LUT. What we do is, for each pixel in the input image, we get that pixel value, we find corresponding pixel in the LUT image, we save the updated pixel value in output bitmap, and we repeat this for all pixel values, and finally we get the output bitmap. This is the gist of algorithm that our custom script needs to understand. So rest of the things seem pretty straightforward. This is the iteration, but like this step, finding corresponding pixel in LUT image, is a bit complicated. Looking up pixels in LUT images, and this is probably why I'm doing this talk. Like, so this next section, it is going to be a bit maybe theoretical and only for reference purposes. So if in future you come upon a point wherein you have to implement image filters in your app, then I am assuring you this section might come in handy at that point. So we have this square LUT image which is 512 cross 512, which has these pixels and all these things. So I had to make sense of like this input LUT image to be able to understand that, like, given an RGB value, any value, for example, like maybe 127, 127, 127, how do I look up that value in this table? Like, where would my 127, 127, 127 be here? So in order to understand that, let's divide this into three different channels, this image, that is red, blue, green and blue. So if you see the red, these values, they increase in each box from left to right. These green values similarly also increase in each box from top to bottom, and this blue value is actually increasing from the top left box to this, like this is 0 for blue and this is 1 for blue. So in order to find a particular RGB value within this, what we need to understand is, like, the blue will give which square to pick, and the green and red values within that square will give me the x and y coordinate. So let's take an example to understand that. Input pixel is this 127, 127, 64 LUTs. Because we know it cannot process 256 colors, so each value needs to be divided by 4. So we divide by 4 and we get this value instead. So the blue, so square within the LUT to pick is the 31st square, and the green and red would be the x and y, that is 31 is x and 31 is y within that 31st square. So let us look at how that looks like. So we firstly get 31st square from blue value, and using this we get 31, 31 within that square. So this is the value that will give me the output value for this particular 127, 127, 127 RGB value that I started with. So this is the what is like going on behind this square LUT image. So so this algorithm is fine, but my Renderscript function, it understands the value of x and y, which is like this coordinate. So how do I convert it, convert all this algorithm into x and y values? It turns out this is how it looks like. And if you want to make sense of this algorithm, all the theory that I just talked about, if you go back and listen to it, then you'll understand, like, and if you look closely, then you'll understand what's going on. So I can get the x and y values using this like algorithm. Once I get the x and y values, then it becomes like within our Renderscript, it becomes a matter of just like keep using this alpha, and we can get this x and y coordinate pixel within this LUT. And these kind of goodies come in with our Renderscript, like we can modify multiple channels simultaneously, and like there is more to it, but yeah, like so this is all I had to do to get this output value, and we do the same thing for all our pixels, and it works. Congratulations. So this is the pipeline that we just implemented. Congratulations. So let us now put it through our transparent test that we had, and turns out it failed again. But why it failed now? So I started looking into it, and also again a friend from a different platform pointed out that it could be because of pre-multiplied alpha. So what is this pre-multiplied alpha? So if you want to know more about it, like I'll just like briefly mention. So this is this good blog called The Curious Case of Android Pre-Multiplied Alpha. So it turns out when Android is dealing with transparent images, for example in this one there are two images, how it does this is like it will multiply our destination image with a value 256 minus the alpha for source, and will add the source and it will multiply it with alpha for source and 1 minus alpha for destination. So in order to optimize this, like what Android does is it pre-calculates these values, because it knows that this is how it's going to render. So it pre-calculates these values, and this is how it stores transparent images. So it pre-calculates, so alpha is pre-multiplied on these like transparent images. So which is fine, and Android does it for optimization and improvement purposes. The issue is, like when we look up an input pixel in LUT, we should be looking up RGB value, and instead what we're doing is we're looking up a value which is RGB multiplied by alpha. So we get the wrong lookup value. So the solution is like one way is like we can tell Android like to not pre-multiply at all. So but that is also not good. It is doing it for a purpose, and like we also want to make use of like those optimization techniques. So instead what we do is we just handle it ourselves, and it is not a big deal. What we need to do is we need to add this unpre-multiply step. Like after we get an RGB value in our pipeline, we do something called unpre-multiply, and then find that corresponding pixel in the lookup table. How we can do that? It is not too difficult. We just like calculate the value that we need to divide our R value with, which is using the alpha of input image, and we do the same thing for RGB values. So we get our modified RGB values, and now we use these modified RGB values to calculate x and y for our LUT lookup. And once we get this x and y, we do the same thing, like we look it up in the LUT table. Now let's put this through transparent test. And finally, this transparent test is paused, and I cannot believe how happy I was at that point. Like, I cannot just explain. But yeah, not so fast. So everything was going on fine, and our transparent test also passed. So looks like our at this point another platform, our web team, they created a reference implementation wherein they produced a bunch of results, and for some reason I found out that their results were a bit better. I'll show you what was the issue with our results. So this is the output that I got for one of the filters, one of the black and white filters. And this was more prominent in black and white filters, to be frank. So if you look closely, you will see there is a bit of banding. And let's try to explain why this banding happens. I briefly hinted upon this, but let's try to reiterate. We have an input image and we have an LUT image. What happens is, input image has colors from 0 to 255, and we only have values, for R we only have values from 0 to 63. That means that all the first 0 to 63 values for R, or just the four first values, 0 to 0, 1, 2, 3 map to 0, and the next four values map to mom, and the next four values map to 2, and so on. So for four colors, each set of four colors, we just have one color to map to. So that is why we get these banding effects. So if you remember, when we saw that example, what we do is, for our RGB values, we divide it by 4. So this is where this issue comes from. So what I just explained, you can clearly see that 64 LUT is actually a lossy technique. If we pass in our input image through this LUT algorithm, we'll lose some pixels. And how we can fix this is we can fix this by a simple mathematical solution, which we all must have read about in our mathematics classes, but we usually do not implement all these things. But yeah, we can do that in this purpose, for this purposes. So what is interpolation? Given 2 points, for example x0 y0 and x1 y1, we can find a middle point in between which will be a result of interpolating between, for example in this case, linear interpolation in between these 2 points. So but our lives are not that simple. So this is what our teacher taught in class, and this is what comes in our examination, because we do not have just x0 y0, we have x0 y0 z0, that is RGB. So given RGB, R1 G1 P1 and R2 G2 P2, two values, we want to interpolate between these two. So for that we need something called trilinear interpolation, and that is what we did. So if you remember, when I talked about script intrinsic 3D LUT class, in its definition it also said that it provides interpolation out of the box. So if that solution had worked, we didn't have to go through all these troubles, but it didn't work. So now we need to implement this interpolation also, but no issues. If we did just that, and if you want to also implement interpolation, then you can also refer this book called Computation Color Technology by Henry R. Kang, which explains this in pretty detail, and these are the sources for it. So this was our result without interpolation, and you could see banding. So after interpolation, now there is reduced banding, so the results are much better. So this was with trilinear interpolation, but there are other interpolation techniques also, so we could also use that to improve the results, but this worked out just fine for our purposes, so we are happy with this. So yeah, this is us at that point when interpolation worked. So we just added an extra step in this pipeline, that after finding the corresponding pixel in LUT image, what we do is we also find the nearby, for example, if my color is mapping to a value 0, I also find 1, and then I interpolate between these two values, and then I get the updated output pixel. So then like this interpolation worked and everybody was happy, but like there were other minor issues. For example, like after fiddling with the app for a few days and everything, like living in the world of dream world that everything is working, I randomly started getting crashes, and like 2 days later I see this stack trace, and like this was absurd. Like this is a stack trace for Renderscript, and there are I see a bunch of hexadecimal addresses, and like there is a faulty address and all those things. And like I tried a bunch of different tools. I asked around at various different Slack groups and everything, but like people did give me certain tools to analyze these memory addresses and stuff, but like I couldn't find a good solution. But then I just like started backtracking, like how we could get a faulty address. So I started thinking that like with C we could get a faulty address, like if we are accessing maybe something with a pointer, like only using that we could get a faulty address. So as it turns out, I thought that it was array index out of bounds, because that is how we could be accessing a wrong memory address or something. So what I did, I clamped a bunch of values for arrays, and it turns out it fixed that crash, fingers crossed. And yeah, just kidding, it did fix that crash, and I never came across that. But yeah, it was hard to figure out. And then the next thing was like LUT formats. So until now in this talk we have been talking about this like square LUT image format. So this was our expectation, and this is what the designers gave us. Like for a moment, I mean at that point I was like okay, but like there is no need to panic. So this is actually a different kind of an LUT image, which is called HALD format. So just like we talked about square format, like this, let's divide this and like look at what's going on behind this HALD format. So as it turns out, for red it increases like this, green increases from left to right over the whole image, blue increases from top to bottom, and so on. So after a lot of analysis, who am I kidding, after a lot of hidden trials, I came across this formula for the new x and y that we could calculate. Yeah, maybe like analysis plus hidden trials, I could say. But yeah, this works, and I could not find it anywhere over the internet. So this is a very good reference kind of a formula that we can keep. So this particular formula fits perfectly within our pipeline for this finding corresponding pixel in LUT image. So I just replaced that particular step with this new step, and congratulations, we have successfully implemented HALD format, and we are again really happy. And finally, this is the output of all this hard work. So this is actually a GIF from our own over app, and this is how it looked like at that point. So we have a bunch of filters that we can apply, we can change its intensities and everything. So yeah, that was using Renderscript. And then what happened is like our tech stack, like our whole team, we migrated to use OpenGL, because OpenGL is much faster than Renderscript as a solution. So we had to migrate filters also now. But like OpenGL, like all this these things that I talked about, like unpremultiplication, interpolation, like still hold true for OpenGL implementation also, because like all these concepts are still the same. But like because it's OpenGL, so instead of writing a script, now we had to write a fragment shader, and that is exactly that we did. We used similar concepts. What we do is like this is just a function that we can use. This is the input color, and we're going to return an output vector 4. So we get the alpha from the input color, we unpre-multiply it, and then when we use the lookup color by looking it up using this texture function within our lookup table. And just like there is something to keep in mind, if we bind this 3D LUT in the right way, then we can actually make use of out of the box interpolation, trilinear interpolation with this OpenGL texture function. And that is what we do exactly. We after getting this lookup color, we return it. Like, this is all that I had to do. So as I just mentioned, we could get interpolation out of the box, and this also runs on GPU, and it's even faster than Renderscript. So now I mention a bit of like references like that one could look at, and where we can go next from this. Like, this is my friend from the web team. He implemented these filters in Go. This was the reference implementation which had like good results and stuff, something. Then there is also in addition to image formats like HALD and Square, we also have .cube file format that if we want to make this algorithm universal, then we can look at. And we could apply a better interpolation technique and see how if the results are better. So finally, given an input image, we can apply a lot of image filters to get filtered images. And yeah, finally, 감사합니다. Thank you for attending this talk. I hope you learned something from it, and I hope it helps.